1. Meet the machine. What the AMOC actually does. Before the diagram, stand on a winter ferry deck in the North Atlantic. Your cheeks sting, your gloves ice over, and the wind tastes metallic. The ocean is breathing heat into the air you're sucking in. Right then, right there. That warmth didn't appear by magic. A hidden engine dragged it thousands of kilometers north and is handing it to the sky above you, like a quiet furnace under the weather. That engine is already running weaker than it used to. This isn't a geology class timescale, it's a grit bill timescale. Start at the surface of the tropical Atlantic where the sun is relentless and the wind is steady. Warm, salty water peels northward along invisible lanes. As it travels, some of that water evaporates. The salt stays. The surface gets saltier, denser. By the time it reaches the subpolar North Atlantic, south of Greenland, around Iceland, the air above is cold and dry, especially in winter. The ocean coughs heat into the sky. The water cools, grows heavier, and begins to sink. Sinking isn't a metaphor here. In certain regions, water columns overturn like an escalator running in reverse. Dense water dives 2-3 kilometers down and flows south in the deep, a slow river beneath the surface. That's the overturning. The return path eventually loops around the tip of Africa, meets currents from the Southern Ocean, and after long detours and upwelling, finds its way back to the surface. It's a global loop, but the Atlantic is the loudest part of the heartbeat. Why does this matter for people? Because that northbound surface stream ferries about a quadrillion watts of heat toward Europe. It doesn't warm Paris by itself. The winds and the jet stream do plenty, but it sets the background state. With this heat shipment, winters in Northwest Europe are milder than they'd otherwise be at those latitudes. Storm tracks and the position of the jet stream lean on the temperature patterns the AMOC helps maintain. Farmers plan around spring thaw. Energy systems assume certain winter loads. Airports expect certain crosswinds. All of it borrows stability from this ocean engine. Salt is the quiet co-star. Evaporation pulls fresh water into the sky and leaves salt behind, boosting density. Cooling at the surface boosts density again. That pairing, salinity and temperature, decides whether water will sink. Change the recipe, and you change the sink. If the surface freshens, the water can stay buoyant even when cooled. If it doesn't, shed heat efficiently to the air, because a fresh, stratified lid blocks mixing. Deep water formation stutters. The AMOC also nudges the planet's rain belts. Shift heat in the Atlantic and you move the equatorial band where air rises and clouds burst, the intertropical convergence zone. That ripple reaches the Amazon's moisture supply and West Africa's monsoon. It ties into hurricane formation zones and the behavior of extratropical cyclones riding the North Atlantic storm highway. What happens between Newfoundland and Iceland doesn't stay there. Now the gut punch. This isn't a gentle slider you nudge a notch and watch it settle. It behaves like a switch. The AMOC shows hysteresis, multiple stable states under the same external conditions, depending on its history. Push with enough fresh water and it can snap to a weaker mode or a collapsed one. Ease off later and it doesn't snap back. The path down and the path up are not the same. That asymmetry is why this matters to your next decade, not your great-great-grandkids. You can flick it off far easier than you can flick it back on. There's a reason scientists still argue about the details. The ocean is messy, winds shove currents around, eddies, spinning features the size of cities, shuffle heat and salt. Some of the sinking happens in narrow straits and on continental shelves that global models have traditionally blurred. But the broad strokes are clear. Warm, salty water goes north. Cold, dense water goes south below. The exchange moves a massive amount of heat, and the balance rests on not diluting the northern mixing zones with too much fresh water. Think of a kitchen, sink with the drain half clogged. Water still goes down, but slower. Now you start adding soap until foam builds up. The foam is light and insulates. Suddenly the drain chokes, not because the pipe changed, but because the surface layer did. For the AMOC, the soap is fresh water from melt and rain. The foam is stratification, that layered ocean where the top refuses to mix with the cold below. When that lid clamps down over the Labrador Sea and parts of the Nordic seas, the deep engine hesitates. Meanwhile, the atmosphere adjusts fast. As the subpolar ocean hands over less heat, the sea surface pattern changes, cooler south of Greenland relative to the surroundings. Pressure fields reshuffle. The jet stream shifts and blocks. Europe gets longer winter cold spells, while the planet as a whole keeps warming. That paradox isn't theoretical. It's the same pattern showing up in recent winters and reanalyses. Trace the heat paths and the headline makes sense. And downstream, the deep return flow slackens. That affects sea level along the U.S. East Coast, because a strong AMOC pulls water mass and lowers relative sea level by altering the pressure gradient. Weaken it, and the gradient relaxes, water piles up a bit against the shore. Add storms to that, and you feel it in basements and insurance premiums. This machine runs quietly, with no on-off switch labeled in bright paint. But it has thresholds built into the physics, density differences, mixing rates, the geography of basins and sills. Cross those, and the mode changes. The unsettling part is that nature has done this before, abruptly, when a big freshwater pulse hit the North Atlantic. We'll go there next. 2. The kill switch, freshwater from melting ice. To see the finger on the switch, look north. Greenland in summer sounds like rain hitting metal, but it's meltwater punching through ice. Rivers form on top of the ice sheet, dive into blue shafts, and blast out at the coast. That water is cold and fresh. It pours into the Labrador Sea and the Erminger Sea, right where the AMOC wants dense, salty water to sink. Add the Arctic to that. Sea ice that used to freeze hard and thick now shatters earlier, and when it melts, it leaves a fresh sheen across the surface. Fresh doesn't mix like salt. It floats and it insulates. Put enough of it over the North Atlantic and you build a lid. The ocean still tries to shed heat to the winter air, but the exchange slows. The top layer stays lighter, stubborn. Below, the water holds on to warmth. The overturning engine needs cold, salty surface water to fall. Instead, it sees a cap. Sinking falters. It's not just ice. Big rivers are shifting their loads. A warmer atmosphere drags more moisture out of the tropics and wrings it out at higher latitudes. Storms deliver heavier rain to the subpolar Atlantic, sweetening the mix further. In the Nordic seas and along the Greenland-Scotland ridge, the delicate balance that feeds deep water formation tilts toward buoyancy. Stratification thickens. That's the lid snapping tighter. We've seen what a pulse can do. At the end of the last ice age, a lake's worth of fresh water rushed from the Laurentide ice sheet into the North Atlantic. The climate flipped in the Younger Dryas. Europe plunged into cold within a human lifetime. That was a bigger slug of water than we're adding today, and the geometry of the Ice Age Atlantic was different. But the lesson is blunt. If you lower salinity enough in the wrong place, the overturning can stall fast. Modern instruments don't tell a simple story at one spot, but zoom out and patterns line up. South of Greenland, sea surface salinity has dipped over recent decades in key formation regions. The Labrador Sea, the Erminger Sea, parts of the Nordic seas. Argo floats feel the stratification. Warmer layers trapped beneath fresher caps. Meanwhile, satellites that weigh Earth's gravity field like Grace and Grace Foe show mass draining from Greenland year after year. That fresh water has to go somewhere, and it shows up at the surface. There's a quiet accelerator in this mix. Several of Greenland's big glaciers don't end on land. They end in the sea. Beneath their floating tongues, Atlantic water has been sneaking in. Water a degree or two warmer than it used to be at depth. That warmth melts ice from below, thins the tongues, speeds the glaciers, and sends more ice and meltwater into the fjords. The more fresh water that exits, the more the local ocean stratifies. The more stratified it becomes, the less winter can vent heat upward. That allows the subsurface Atlantic water to stay warm and keep eroding the ice. It's a feedback loop, and it feeds the kill switch. Add another lever, wind. The subpolar gyre, the vast swirl south of Greenland, breathes in and out as atmospheric patterns change. When winds spin it into a tighter, more retentive state, it can trap fresh water, corral it over the very basins that need to be salty to sink. Those years, deep convection weakens. When the gyre relaxes, the cap can spread and thin. On top of the long-term freshening trend, these wind-driven pulses act like taps opening and closing over the mixing zones. Each factor alone is manageable. Together, they push a system with memory toward a threshold. And because this is a basin-scale machine, the signs don't flash like a red light on a dashboard. They appear as a cool patch in a warming map, a cold blob south of Greenland, where less warm water is arriving at the surface. They appear as a subtle rising of sea level along the U.S. East Coast, consistent with a slackening deep return. They appear as an ocean taking longer to heal from winter storms that used to mix it clear. None of this is distant in time. Freshwater input from Greenland has increased markedly since the 1990s. Arctic sea ice has lost more than half its summer extent since the late 1970s, changing how and where freshwater enters the Atlantic gates. Precipitation maps show the subpolar region getting wetter in winter. Observations and reanalyses point to stronger surface stratification trends, where it hurts overturning most. The picture isn't perfect. Local salinity can spike or dip from one year to the next. A harsh winter can tear open patches and spark deep convection again, briefly. But the baseline is moving. The cap is thicker, the deep is warmer, and the places where heavy water used to fall like stones are sputtering more often. So if you're looking for the finger on the switch, it's a hand, ice sheets, sea ice, rain, rivers, winds, and subsurface heat working together. The question now isn't whether they matter, it's whether the engine is already stalling in ways we can diagnose in time. The early signs are out there. The next step is to read them. 3. The 3 tripwires, signals of destabilization. Start with what you can see from space. Today, not in a simulation. In a world map of warming seas, there's a stubborn blue bruise south of Greenland, the cold blob. It shows up in NOAA, Hadley, ERA datasets. It shows up in the latest anomaly maps you can pull up on your phone right now. Everywhere else runs warmer over the last century, but that patch cools relative to its surroundings. It's not magic, it's a missing delivery. Less warm water is reaching the surface there. That's the first tripwire, a fingerprint. Many studies associate with a weakening AMOC, the same dipole pattern that pairs subpolar cooling with a warmer stripe along the shifted Gulf Stream. You don't need to trust any one model to notice the anomaly. It's lodged in observation maps year after year, and in recent winters it has intensified against record-breaking global ocean heat. Make it concrete. Airlines reroute around turbulence bands that set up along sharper temperature contrasts near that patch. Fishermen out of Newfoundland talk about green water lines where the temperature drops and fog clings a day too long. Weather desks in Europe watch that blue oval like a pressure cooker valve because it sets the tone for downstream blocking. This isn't a contour plot curiosity. It's a live feature nudging the weather you step into. Why does that matter to people? Because that patch isn't just a color on a chart. It's the sign of less ocean heat released into the atmosphere where European weather is forged. Shift that background field and you tug on pressure patterns, storm paths, and the seasons people rely on. That cold patch is a quiet, persistent note played under winter forecasts, and it keeps getting louder. Now pan from satellites to sea level along the U.S. East Coast. Again now. Tide gauges from Norfolk to New York tell a story of water creeping higher, faster than global averages at times. Nuisance floods have multiplied within a single career for harbor masters. Part of that is ice melt and thermal expansion, but part of it is dynamic. When the deep southbound limb of the AMOC slackens, the north-south pressure gradient across the Atlantic eases, and water stacks up against the coast. Think of it as a barometer for the Atlantic's muscle. That's Tripwire 2's cousin, because the same physics show up in another metric, the sea surface height and density gradient across the Gulf Stream. Oceanographers watch the tilt of the sea surface across the current and the shear of velocity beneath. When the Gulf Stream weakens, the slope flattens a touch and coastal sea level nudges up. Long records stitched from altimetry, tide gauges, and hydrography suggest episodes of weakening over recent decades, consistent with a gentler AMOC. Meanwhile, moorings strung across the Atlantic at 26.5 degrees north, the Rapid Array, have tracked notable year-to-year swings and a long-term decline from the early 2000s baseline. It's not a straight line, and it's not decades long yet, but paired with indirect proxies, it adds weight. And it's happening in the only sustained direct observing line we have. About those proxies. We can't put a flow meter on the entire overturning for the last 100 years, so scientists use fingerprints that physics predicts. The cold blob is one, the gradient across the current is another. There are also density reconstructions from the subpolar North Atlantic, sediment records that reflect past deep current strength, and the growth bands of corals that preserve changes in water mass properties. Different archives, different methods, same direction. The AMOC today is likely weaker than at any point in centuries, perhaps a millennium. Each line has caveats. Together, they form a picture you can't wave away with a single counterexample. Now for the third tripwire, the one that hides in noise but is flashing in real datasets. As complex systems approach a tipping point, they tend to recover more slowly from small nudges. Statistically, that shows up as critical slowing down, rising autocorrelation, and rising variance in time series that track the system's state. In plain terms, the system's wobbles last longer and grow larger because it's losing its restoring force. Researchers have applied these early warning indicators to AMOC-sensitive fingerprints, including reconstructed temperature and salinity contrast across the Atlantic. They report trends in those indicators consistent with decreased resilience, and some studies go further, estimating a mid-century window for a tipping event under current forcing. That's a bold claim, so let's be clear about what's measured and what's inferred. We do not have a century-long direct measurement of the AMOC's full strength. Moorings like rapid date to the 2000s. The Gulf Stream itself is just one part of the overturning, not the whole. Sea surface temperatures can be pushed around by winds and aerosols as well as currents. Early warning statistics can be fooled by the choice of window or by unrelated variability. Those are real limitations. But here's why the inference remains strong and urgent. The cold blob persists across methods and datasets and lines up with known dynamics of reduced heat import. The sea level and gradient signals have the right sign and appear alongside independent evidence of subpolar freshening and increased stratification where deep water forms. The moorings see variability that matches wind-driven changes, but also a background easing. Paleoclimate analogs show the AMOC has two distinct modes and can jump. And the early warning metrics aren't alone. A newer, physics-based indicator looks at the freshwater transport at the southern boundary of the Atlantic. In models that actually tip, that transport passes a minimum on the way to collapse. Reanalyses hint the real ocean may be moving in that direction, and that's a real-time budget, not a vibe. Bring those threads together and you get 3 alarms you can watch today. A visible fingerprint on the sea surface, a mechanical slackening registered in gradients and coastal water levels, and a statistical heartbeat that's slowing. Add cross-checks, sediment drifts that thin when deep currents weaken, coral geochemistry that records water mass shifts, isotope patterns that track past overturning changes.